and then you can just like this way, because we like to know the vertical forces on what BC at points B and the vertical forces. We have the BX, BY, BX. We can do this, right? CY, CX. We can do this way, okay. And this is the FBD for BC. How about its KD? KD, we know that BC is actually doing curvilinear translation. So for BC, so just like do this way. This is C, this is B, MAG. So MAG will be MAG. So how about its AG? How about AG? We know that when the rigid body is translating, the displacement, the velocity, the acceleration of any point should be equal with each other. That means this is a point G, my center, they will have the same. Just wait me a moment. Sorry, one moment. I'm back. Okay. So here, because BC is doing curvilinear translation, so the my center of the what be ABC, the G point G, will have the same velocity, same displacement, same acceleration with point B and point C. For point B, so point B and because AB is rotating, right? AB is rotating, that means B have a circular path. So B, the acceleration should have B, we have the AN, normal acceleration, and AT, tangential acceleration. Here, fortunately, because it's a constant angular velocity, that means the angular acceleration equal to 0, there's no AT, only AN. What? Only AN. This AN, we can calculate the normal acceleration using point B or using point C. It will result in the same solution. So this is MAG, right? So accordingly, we can have the same, we can in normal direction, the x component, normal direction, the normal component of the real force will equal to MAGN, tangential, and sigma mg equal to 0, right? So here in when BC will always remain, because BC always remain horizontal while moving on a curvilinear path. So just as we said, BC is doing curvilinear translation, so it will have the same acceleration of point B and point C. And so for BC, this will be CXCY, BXBY, and G. This is a real force. We use red to indicate the real force. This will be MAG. Okay, you need to know that this one is actually the inertial force. Okay, MAG. Okay, is a kinetic force. Okay, we call it kinetic force or the inertial force. Okay, kinetic force. Okay, and because it's a constant rotating, that's why angular acceleration equal to 0. That's why tangential acceleration equal to 0. That's why here we only have MAN, okay? And AN is equal to R omega squared. That's why here. And accordingly, we can apply the equations, okay? Sigma Fy, and we will have Cy, sigma Fy, equal to MAGY. AGY is given, this is MAGY, and sigma Cy plus By minus MAGY minus G will equal to 0. And also accept the scalar equations for the force. We also can have the moment equation. The moment equation again and again. We just address that they are the equivalent system. The FBD and the KD, they are equivalent force system. So for any point, the moment about any point should be equal with each other. This one is a moment about point C. You can choose point G. It's up to you. Okay. You can choose point G, but if you choose point G and CY, BY will still appear. But if you choose CY, there will be only BY. One unknown will have the moment, right? That's why we take C. Okay, when we take C as the moment center, the wheel force system, the moment of the wheel force system about point C should equal to the moment of the kinetic force system about point C. Okay, so this one here, you see, when we calculate the moment about point C, Cx, Cy passing through point C will produce no moment. And this one, the weight and will have the moment about point C. So this one will have the moment about point C. This is for the weight, the moment, because this one is actually the moment arm of the weight. And BY will have the moment about point C. Okay, this is the moment arm of BY. And here, right hand side is actually the moment of the electrical force. Okay, the moment of the kinetic force about point C. The moment of the kinetic force about point C here, we only have MAN. Okay, that's why we have here. So solving this equation, only BY is unknown, so we can find out BY directly. And then in right direction, we can find CY. Okay, but can you find CXBX? Can you find CXBX? No way, I can't. We only know Cx plus bx equal to 0, but here we can't find Cx bx. But later on, if you can analyze AB, just like for AB, right? This is A, and so we draw FBD. This is FBD, right? And for B, again, we have bx prime, by prime, right? And A, and for this is FBD. We also have KD for AB, and you can find bx. Okay. So this is with horizontal. Okay, we can do this when theta equal to 90 degree. This time, okay, when theta equal to 90 degree, just like here, we go back when theta equal to 90 degree. Okay, so BC is still horizontal, remains horizontal, but this time, sorry, should be here. This time, and the MAG should be point to the B. Okay, again, we only have AM. AT, tangential acceleration, should equal to 0. So for the K kinetic force, we only have the normal force. Okay, normal kinetic force. So we still can apply the equation of motion. We take point C to calculate the moment. Again, we still have the moment of the real force about point C equal to the moment of the kinetic force about point C. Here is equal to 0. Why is equal to 0? Because for the kinetic force here, MAN, it passes through point C. So this one equal to 0. We can find BY easily. Again, we can just write down the right direction. Okay. So this is for translation. Okay. This is for which body is doing translation. We will continue study about when it's the rigid body is doing rotation, is rotating. So let's share it. Okay. Actually, no matter its translation, no matter its rotation or general motion, we have the same equation motions. Okay, so I just don't want to spend time on the applications. You can do it by yourself. Okay, and here when a rigid body rotates about a fixed axis perpendicular to the plane of the body, at point O, the body's center of gravity G moves in a circular path, right? This one definitely we know that when it's rotating, every point will have a circular path. So for the point G, it will have the tangential acceleration and normal acceleration, right? So for the kinetic force, we will, instead of using AGX, AGY, we use AG tangential, AG normal. And because tangential acceleration equal to the radius of the mass center times angular acceleration, and the normal acceleration of the mass center equal to the radius times the angular velocity square. So the kinetic force. So the kinetic force will equal to m mass times normal acceleration, and or the kinetic force, tangential kinetic force equal to m at g alpha. So, but again, we still have sigma mg equal to ig alpha. That means for here, instead of in x y axis, we use the resultant force in the normal component of the resultant force. This one we calculate this based on the FBD because it's the normal component of the real force system. And this one will be the normal component of the kinetic force. Okay, this one will be the tangential component of the real force system. This one will be the tangential component of the kinetic force. And this one, again, this one will be the moment about mass center of the real force system. This one will be the kinetic moment about mass center. And again, we said we can take any point, right? Just like point O, just here O is rotation center, or A point, just as you wish. And it should equal to sigma m k O, right? This one we know that they are the equivalent force system, so they will should have the same moment about any point. Okay, so here instead to take the moment about mass center, we take the moment about point O. So this one will be the moment about point O by the real force system. You calculate based on the FBD. That's why we always said FBD is really, really important. Okay, the force analysis. Okay, very important. Here, this one is actually the moment about point O of the KD of the kinetic force system. Here, except Ig alpha is actually the kinetic moment, right? Ig alpha is the kinetic moment. It will result in the same moment about any point, about point G, about point A, O, about point A or B. It will be same here. But except the moment, kinetic moment will also will the kinetic force will have the moment about point O. We have the kinetic force normal and tangential. We know because the normal kinetic force passing through the point O, the moment arm equal to 0. So this one will have no moment about the point O, but the tangential component will also have the moment about point O. Its moment arm is Rg, and its magnitude is magt, and the tangential acceleration equal to Rg alpha. So we will have this one. But what about this? What about this? IG is the moment inertia about mass center plus MAG squared. What it will it be according to the parallel axis theorem? This one should equal to IO, right? The mass moment inertia about point O, well, according to the parallel axis theorem, the mass moment inertia about point O equal to the mass moment inertia about the mass center plus mass times the perpendicular distance between the two axes. Right? So what we will have? We will have sigma MO equal to IO alpha. Okay. So here for a rigid body which is rotating, you can write down the two scalar equations for the force. Okay, because for the two equivalent force system, they should have the same resultant force, and also for the force system, they should have the same moment about any point. Okay, so instead using the moment about mass center, generally for a rigid body which is rotating, it will be much easier to choose the rotating center. Okay, so we have sigma MO equal to IO alpha. We have derived it. Okay, sure, it's a little bit fast. You need to do that by yourself. So when you review, you just go through all the process. Okay. But anyhow, always remind yourself they are two equivalent force systems. When you understand this, and things will be easier because you will use what you have learned in statics. When there are two equivalent force systems, what kind of relationship they should have? Same without force, same moment about any point. Okay. So to do the to solve the problems involving the collection of rigid body rotating, so we will have the same procedures. First, the coordinate system, and you need to specify the sign and direction of the acceleration of the mass center. Okay, because you have sigma f. Because you have sigma f equal to mag, right? And then after the coordinate system, we know that everything everything you will have to be calculated according to FBD and KD. So you need to draw FBD and KD, and then you can calculate the mass moment inertia of AIG, the mass moment about the mass center, or the mass moment inertia about the rotating center, and then write down the three equations. Okay. Okay. And sometimes we need to apply the knowledge of kinematics to relate the unknowns. So let's solve together. A rod with a mass of 20 kg is rotating at 3 meters per second at the instant shown. A moment of 60 Newton meter is applied to the rod. We need to find the angular acceleration alpha and the reaction at the pin O when the rod is in the horizontal position. Yeah, this rod is rotating. Okay. We need to find the angular acceleration and the reaction at the pin O when the rod is in the horizontal position. So we can just establish the coordinate system, sure, horizontal x and y, right? Or x, y, as you wish. Just follow the same specification, okay, in your calculation. So that's enough. And then draw FBD, draw KD. FBD, the weight, right? The weight, and at point O, OX, OY, right? Anything else? No more, right? For the real force system is FBD. But except FBD, you also need to draw KD, right? what will be the KD? I use another color to draw KD. What will be the KD? Because it's rotating, so it will, because it's rotating here. Because it's rotating, and so the my center we use G will have a circular path, right? We'll have the circular path. It will have AGN, right? I use AN. And AT, right? Tangential. So we'll have MAN, MAT, right? Sure, you will have, you can have IG alpha, right? IG alpha, right? Or you just don't use IG alpha, you use IO alpha, that will be okay. You use IG alpha, right? And then there are two equivalent system, and you should have sigma Fn equal to MAN, sigma Ft equal to MAT, and sigma Mg or Mo. Maybe we choose Mo, right? Because when you choose sigma Mo, OXOY will have no moment about point O, only the weight have the moment about point O. How about the kinetical moment? It will equal to I or alpha, right? So things will be easier. So since my center G moves in a circle of radius, its acceleration will have the normal acceleration and the tangential component act downward at the perpendicular to RG. Okay, so this will be FBD, right? This will be FBD, and this will be KD. You see, this is its tangential acceleration. This is normal acceleration of the mass center. IG alpha is the kinetical moment. Okay, they are equivalent force system. So we will have the equivalent without force, equivalent moment about any point. So here you define to the left as positive. So it's up to you, okay? So for the wheel force system, we will sigma Fm. Sigma Fn, we only have On, okay? On and equal to Man. This is, they are equivalent, okay? So this for the FBD in normal direction, only On, and in KD, only MAN, right? And we can find out OM. Similarly, in tangential direction, we have OT, we have W, right? OT and W. And for the KD, we have MAT, right? The tangential acceleration times the mass will be the tangential component of the kinetic force. So this one. And we, except for the two scalar equations of the force, we have the moment about point O should be equal with each other. So sigma MO. And this one is calculated by the wheel force system. Only the weight will have the moment about point O. And this one, well, we will have the IG alpha, or you just equal to IO alpha. We already derived this, right? Right. Here is IO alpha, right? We know this. And then we can find out them directly. Okay. So I want to ask you, here the what is horizontal. How about if it's perpendicular, just like this way? Can you do this when it's perpendicular? Can you find the alpha? Can you find the alpha directly? This is O. So how about if in vertical? So again, with vertical, it's OX, OY. Maybe you can use the normal and weight, right? This is the FBD. and draw KD. What will be the KD here? For the mass center, MAN, right? MAT and IG alpha, right? And again, you will have sigma Fn equal to MAN, sigma Ft equal to MAT, because here you see I use OT or OM, yeah, or OX or Y, and sigma M O equal to I O alpha. So can you tell me when it's vertical, with the water is vertical, the acceleration, angular acceleration should equal to what? Can you calculate the angular acceleration? Can you calculate the angular acceleration? Can you try to calculate the angular acceleration when it's vertical? You can use this. Sigma MO equal to IO alpha. Right? For the wheel FBD, no moment about point O, because the force, reaction force at point O passing through point O, and the weight also passing through point O, so sigma MO equal to 0. So at this instant, the angular acceleration equal to 0. Okay. Here, if a rigid bar of length L is released from rest in the horizontal position, the magnitude of its angular acceleration is at maximum when theta equal to 0, theta equal to 90 degrees, theta equal to 180, theta equal to 0 and 180 degrees. Can you try to choose? It's the same, right? We just solve this. The bar or the rod. So can you choose alpha? This is O. So only weight will produce moment, right? Sigma MO equal to IO alpha. So when the wheel forces will have the maximum moment about point O, when we'll have the maximum moment arm, right? So the answer should be D. Do you follow me? Do you have any question? Because you have no reply. This one is very important, okay? And when theta equal to 90 degrees, the horizontal component of the reaction and the pin O is when the horizontal, when theta is equal to 90 degree, what will be the answer? 90 degree. Yeah, 0. Yeah, very good. Because Ig alpha, we found that alpha equal to 0. And so when you sigma fx equal to 0, you will find that sigma fx equal to not 0, sorry, if equal to no. Are you sure equal to 0? Let's do it together, okay. So when it's horizontal, vertical, the weight W, OX, OY. We need to find the OX, right? And then we have MAN, because see, MAN, we have MAT, right? We have IG alpha. We know alpha equal to 0, right? We know that there is no moment about point O. How about AT? AT is equal to R alpha, also equal to 0. So the answer should be A. Very good. Okay, very good. So a drum of mass M is set into motion in two ways. A, by a constant 10-pound force. and B by a block of weight 10 pounds. If alpha A and alpha B represent the angular acceleration of the drum in each case, select the statement. Which one is true? Alpha A larger than alpha B, alpha A equal than alpha B, alpha A smaller than alpha B. You don't know which one. Here, the angular acceleration. So we know that we will have IO alpha equal to, this is for the kinetic moment about point O, and the moment of the wheel force system about point O will equal, this is T equal to TR, right? So if alpha A, alpha B, it depends on the about the tensile force, So this tensile force is equal to 10 pounds. How about this tensile force? Will be smaller or larger than the 10 pound? Will be smaller or larger? Can you tell me? Or maybe you can take this as a system. The IO about this sum, for this one, the IOB will equal to the disk plus the block, right? This one is larger than this one, so alpha B should be smaller than alpha A. So the answer should be A. Okay, I repeat. Okay, I can repeat it. Okay, we can do, yes, we can do in two ways. First thing is will be simple, just like for this one, we know we can write down sigma m o equal to sigma m k o. What does it mean? This is the moment of the wheel force system about point O. This will be the moment of the inertial or the kinetic force system about point O. So for this case will be T times R, right? This will be equal to T equal to 10 pound, right? For this one, if we only consider the disk, will equal to IO alpha, right? IO alpha. So for A and B, we need to know, for this is TA, this is TB. We need to know TA, if TA is larger than TB, we know alpha A will larger than alpha B. If TA equal to TB, alpha A will equal to alpha B. Or TA smaller than TB, alpha A will smaller than alpha B. Obviously, because for the block, this is the weight, this is TB, and because we know that is accelerating, because if you got alpha and the block also go downward with acceleration A equal to R alpha, right? So that means TB should smaller than W. So smaller than TA, right? TB smaller than TA. So we can know that, okay, we know that the alpha, we know that, am I right? We know that A will larger than alpha B. TB smaller than TA. This is one way. Or you can take this one as a system. So for this system, the force W will have the moment about point A. So W times R will equal to the IO. IO will be the system, the maximum inertia of the system about point O times alpha B. The mass moment inertia will equal to the moment of the disk about the point O plus the moment of the block, right? It will larger than the disk, right? So this one we can also know B, right? For the problem. Tension B in the cable in case B is, yeah, already figure out. Smaller or larger, okay? Which one? We just figure out together, right? So which one can you tell me? A or B? A or B? Which one? We already figured out this. In the tension T in the cable in case B is smaller than its weight or larger than the weight. Smaller than larger than the weight for the block. This is the weight. This is T, right? So accordingly, we will have W minus T equal to MA, right? How about the acceleration A? How can you, if the alpha is given, can you calculate the A? Because velocity will equal to R omega. Omega is the angular velocity of the disk, right? So take the first time derivative. We will have A of the block equal to R alpha, right? So T equal to W minus MA. So T, it should be smaller than 10 pound. Okay, the answer should be B. So now it's time for you. The disk of the weight of the disk is given, the watch is given, and omega equal to 8 meters per second. We need to find the horizontal and vertical components of the reaction at pin O when the rod is horizontal. Okay, so here it's fixed, okay? It's fixed, okay? I mean, this, the disc, and this is what, okay? The watch, the length, they are fixed here, okay? That means the disc cannot rotate. Okay, just like you, the rod with the disc, okay, together, we need to, they are rotate as whole entire body to rotate about point O. There is no relative motion between the rod and the disc. Again, solve this and submit online. Okay, solve this and submit online. You need to draw FBD, you need to draw KD, and then you need to apply the equations of motions. You have scalar equations, sigma Fn equal to MAN, sigma Ft equal to MAT, sigma MO equal to sigma MKO. Okay, here, one thing, you need to find out the Mach center, for the seesaw. Okay, how to find the Mach center? How to find the Mach center for this? How to find the Mach center? Actually, if you define the x-y axis, or we can choose the left as positive axis, right? You only need to find the xg, right? How to find the xg? Xg it will equal to sigma m. M will be the total mass of the rod plus disk, right? Sigma mi xi, right? So you need to find the mass center of this seesaw, and then you can find the acceleration of the mass center. Because it's rotating, it will have the normal acceleration and tangential acceleration as usual here. And also, we only say it will omega at this instant. We don't tell you that it will rotate with constant angular velocity. That means, and we don't know alpha is equal to 0 or not. We don't know. Okay. So please solve this and then submit online. Okay.